107. So let's construct the famous homomorphism theta of Fontaine. So let WR be the ring of with vector with coefficients in R. And notice this is a discrete valuation ring, complete discrete valuation ring. With maximum ideal P. And the residue field R, right? So recall that R itself is not discrete valuation ring. It's not a discrete valuation ring. It is valuation ring but not discrete. Okay. So basically the valuation has its target is surjective, or the image of the valuation is rational number. You need the symbol plus infinity. And so we have this isomorphic quotient by P. Exercise 1. OCK quotient by P. OCK is not complete, it's not perfect, sorry. Right, so the idea or question, why not x to the power p equals y to the power p implies x equals y, and hence Frobenius is injective. So let's say this is not perfect. In fact, Frobenius is not injective. Why? This is not true and hence imply Frobenius injective. The answer is, recall that we have a statement saying that Frobenius is injective if and only if the ring itself is reduced. Remember, we proved this exercise. And so notice OCK over P is not reduced. Not reduced. Basically, you have the ableton elements, not to mention p power root of p, right? Just to take a very particular example, so the square root of p, and then squared is p, which is 0. But this is not 0. Right, so it's not reduced actually. This also gives you an example of Frobenius is not injective, so you take p to the power p root of p. then this pth root of p raising to p's power equals p bar, which is 0. But this is not 0. Okay. So remark is that hence there is no evident way to apply the weight factor to lift the JK equivalent map R to OC quotient by P. So this map is just, for example, theta 0, right? Just map x, let's say xn to x0. Or xn to xn bar, x0 bar. There is no evident way to apply weight factor to induce map from WR to OC. Okay. Well, just saying that this is not WOC. But we want such a remap. So let's construct such a remap. Exercise 2. Construct a remap from WR to OCK. So what's in my mind was that, so let me start with xn. And then I would like to map it to x0. Sorry, should not write this. So let's start with here is x. Well, yeah, this is not very easy to write. I would like to write it this way. So this is how to say. I would like to use Teichmuller lift, right? Let's say so. Take element. So the idea is, why not firstly do this, right? Then do this. Question is there a good ring map? Is this a ring map? I mean, let me avoid these. When I say yn map to y, y equals yn, and then map it to, let's say, y0. Is this a good remap or not? I mean, yeah, here I mean y0. Actually, this is just mod p, if you want. Yeah, so this is remap, and the other way, this is also remap. There's projection, some kind of theta 0. Right, this is okay, why not? I guess we going to construct such a map, but in a different manner. Let's see. So I first put on remarks. Remark. So let small a WR. So all the components are in R for any n. So notice a m can be written in two different ways. Depends on which bijection you want to use. Wait, is this just a bijection or actually a ring isomorphism? Yeah, this is actually a ring isomorphism, just two different way, right? So we use this. We use this. So the ring structure is just component wisely multiplication and addition. You can also use this. And with special addition and multiplication, right? Okay, so firstly, the way is to, let me avoid using 1, 2 to preserve it for question index. So the first way to write it is AMR upper index, such that in this case those elements are characteristic 0. For every R, and reading to the power p equals or second way to write it, AMR R integer such that AMR OK quotient by P OK. And again, it's compatible with this transition map of Frobenius. So I'm gonna call this remark 1, and then remark 2. So I'm very used to put remarks with index like this: 1, and then 2. Now let me see, so we have a natural map. As follows, so take any element, use the lower index with the lower index 1, which means think of those elements, written those elements in characteristic P, map it to weight. So for element in WR, again, we are writing it as firstly A and let me say A0, U1, and then you pick any one with, let's say 0, is then returns A0. So we're mapping this to A0 n, A1 n, A n minus 1 n, so there's not at all any condition here. There is no compatible with Frobenius condition because this is in weight vector, but as I said, this is projected with this self product n times. I don't know what's a better way to write this. So there's no problem with this definition. This is still well defined. And this in particular gives commutative diagram as follows. So let's start with WR and then map it by our just constructed map. Let's map to WN. With this transition, with this vertical map quite Fn too. So let's say, let me call this A. So A is mapped to here A0n, A1n, A why are there so many n? Why are there so many n? Wait, why are there so many n? Yeah, no problem. This is just telling this lenses and the angular coordinates, and because the coordinates just this is second position. Yeah. Okay, so the problem is that by our definition this should be mapped to A0 n plus 1, A1 n plus 1, etc. Well, finally n plus 1. And then it's mapped here to A0n, A1n, and finally an minus 1n. Well, what is this map? This map is, how do you get from here to here? Raising to the piece power. Did you see that? So this Fn is just defined to be right, this map, this works. From this, we see that by passing to the inverse limit, we have this So it's a transition map Fn. Right, so each position, so for example in the 0 index component you have this A0 0 and then A01 and then A02 and continue in this position, so every element raising to the p's power gives you the next one. It's actually this gives an element in R. So this inverse limit of this is not W of OK bar, P OK bar, it's not, okay? The inverse limit of this is contained in OK bar. It's difficult to describe in this way. Of course, it's containing W0, OK bar quotient P, W1, OK bar quotient W2, etc. Is it good I talk about this? I'm not sure. Seems like this. I mean, I'm using the fact that R is the inverse limit of this. Okay, bar over P. So as you could say that actually what I want to say is that so let me erase all of this, and then let's just simply say that this map is, yes, it's obvious, but it's constructed probably as follows. So you got your A0, 0, and then A0, 1, A1, 1, and then A0, 2, A1, 2, A, wait, should start with A0, 0, 1, and then 0, 1, 1, 1, 0, 1, n equals 1. This corresponds to A0, 1, and then yes, A0, 2, A1, 2, and then A0, 3, A1, 3, A2, 3, etc. And so this will be mapped to, where are we going to map? We have mapped it to first A0, 1, A0, 2, A0, 3, etc. This is the first element. This is in R. Then secondly, A1, 2, A2, 2, etc. As you could imagine for that. So I'm selecting all the first position, then selecting all the second position, and then selecting all the third position, etc. And conversely, for any element starting here, you could put the first component of the first position here, and then 0, 1, and put A0, 2 here, put A0, 3 here, etc. And secondly, starting from the first position, put the first component of the second element to the second component of the second element, and then put here, you put there, right? This is just a one way to construct a bijection here. Moreover, this is a ring homomorphism. We'll just check that. So actually, this is a ring homomorphism, right, by the universal property of inverse limit. So the inverse limit should have canonical morphisms here and there, and then for any other one which have morphism there should be a unique map. Make this commutative. And then I notice this map is also bijective, and so this is isomorphism. Remark, this is actually a homeomorphism. Of topological groups. If the object on the right hand side of the isomorphism is equipped with the inverse limit topology of discrete topology. On each component. Third remark, let's consider the surjective map. It's denoted by psi. Let's say psi n plus 1 from wn plus 1 OC k to w of n OK bar over P. So this is very easy to see just by notice that OCK quotient P is the same isomorphic to OK bar quotient P. So this map is nothing. What is I kernel? Then how do you describe the kernel? The kernel is then could be described as follows. So P B0 because modulo P is 0. Okay, then the similar thing happens until P n minus 1. Then whatever it here, so all those BI's and the last AN, they're all any element in OCK. Now we'll construct one more rim map. Let's call it omega n plus 1 from W n plus 1 OK CK to OCK. How do you define this? So take any tuple, map it to A0 to the power P to the power plus P times A1 to the power P and minus plus etc. until P to the power n times A0 and n. Sorry. such that omega n plus 1. Okay, so let's just describe it this way. This is a remap. We compose this with quotient map from OCK to OCK quotient around OCK. This gives a map then from plus 1 OCK to OCK quotient p to the power of OCK. Now notice that omega n plus 1 acting on 0 n is here, but if I acting it on elements of the kernel C, this is then this is then obviously 4 into P and OCK. Therefore, what that this implies? Let's look at here. So we have this omega plus 1 OCK. Here omega plus 1 OCK, and then the surjective map p to the power n. And then we have this surjective map through C plus 1 to WNOK bar function. And we notice that the kernel of this actually is contained in is mapped to 0, which means it's contained in the kernel of this, and so this factorize, and we call this theta n. There exists a unique homomorphism such that a diagram commutes. So this theta is not the theta before, because the theta before is from R to a component here. We involve the Reynolds vector. And so by construction, so I'm saying that this is in the kernel. right? By construction of theta n, we have a commutative diagram. The morphism here is Fn. Why? Because you can't fit this part into the commutative diagram here, I think. Why do I say so? Wait. I mean, how about just W, let's say n plus 1 OCK. Yes, just don't touch this part, just copy it, and then here we have the surjective Cn plus 1, which maps A0, A1, An to just A0 bar, A1 bar to An minus 1 bar. Right, this maps to W of N, OK bar quotient by P OK bar. And then here you have surjective map to W minus 1 OK bar. But this is through our Fn, which maps to A0 bar to the power P. A1 bar to the power P, An minus 2 bar to the power P. There are minus 1 elements. And so what is the kernel of this? The kernel of this is whatever N minus 1 bar here. But the kernel of this is of this field elements of the form PB0, PBN minus 1, and then AN, whatever, BI, BN, OCK. And the kernel of Fn is, as you could say, 0, 0 everywhere, and lastly An minus 1 bar. minus 1 and then and so the kernel of Cm plus 1 compose Fn, or Fn compose C minus 1. Cm plus 1 is all those map to here after Cm plus 1, which means Cm plus 1 inverse of this. And so this is actually all those A0, A1, AN, such that so A0 bar equals 0 bar, A1 bar equals 0 bar, but AN bar equal this A minus 1 bar equals whatever. So don't put restriction here. Anything you want, right? So I mean, here you go write this, any element here, any element you want. And so this is just saying that it should be the form P B0, P B1, P Bn minus 2, and then Bn minus 1, and then A. That more, the bigger kernel, more acute. But then now you have to look at this composition of Pn minus 1. Notice this omega plus 1 of this is done by the construction again. PB0 to the power n plus P times P B1 to the power P to the power n minus 1 plus etc. plus P to the power n minus 1 times Bn minus 1 plus P to the power n times An. So what do we want to say that? This is always containing P and minus 1 OCK. So there exists a unique map. Theta plus 1. And so diagram commute mix tells you that this commutes. Okay? So we have this compatible system and pass into the limit gives homomorphism ring, so ring map, which we call it theta from W R to O C K. Lemma. Let's prove this lemma. Exercise 2. 3 maybe, right? This is already 3, I think. Because we have proved, we've constructed the map. Yeah. And now it's 3. Exercise 3, this is the lemma. If X is in the width ring, for X and R, and X and retain this far. With COCK. Yeah, so use the standard notation. Upper index. So the characteristic 0 ring OCK. Then we're going to give a precise description of theta. Theta x is going to be p to the power n times x n. So it's x0, 0 plus p times x1, 1. Right, let me write it down. This is x0 plus p times x1, 1 squared times x2, 2, etc. Right, this is jumping from increasing component of increasing sequence, increasing component of increasing index sequence. So let's first prove this, and then let's come back to our old construction. We haven't really compared with that. Our naive construction of theta. I put an ideal after exercise 2 was stated. So now let's prove from this what do we call natural map above, which is selecting the increasing index component of increasing element. Increasing next element sounds bizarre, but I'm just summarizing the situation. This is the definition. Okay. Then we take xi parenthesis n to be a lifting in OCK of xin, then theta n x0n x minus 1n is, by our construction, actually this could be described easily because it's just the one mixed diagram commutes. So you just describe it here, right? You know how to describe elements, image of it. This is quite obvious. Actually, it's just, so you start with element here, and then got C, got m plus 1. So let me just take time to do this. Okay, so let's say we got a 0, a 1, a n here, right? Then so let me do this, let me put this slightly rightward, and then this is mapped to the construction omega plus 1. Wow, it's 0 to the power p to the power n plus p times a 1 p to the power n minus 1 plus etc. Finally, p to the power n times a n, and this is mapped upwards by c plus 1 to what? To just a 0 bar and minus 1 bar. And this is mapped to, again, a 0 bar, p to the power n plus p times a 1, or if you want p bar, a 1 bar p to the power n minus 1 plus p to the power n times a n bar. And so this is our theta. And you see where it comes this formula. So this is mapped to p to the power I times xin. What we're doing is we first lift it and then we take the bar. Should we do it here? Let me think. Yeah. Yeah. Yeah, theta is mapped to theta is mapped to, here is sin OCQ quotient by p to the power n, but here is sin OCQ quotient by p. So what you really have to do is actually, this is not the same bar, you see, but p to the power n is contained in p. This implies that when quotient by p, this is smaller, that is bigger. What you're doing actually, that's lifting. And you just pick any lifting, and that you define the same map. So what you should do is that pick any lifting, and then finally you take the quotient one more time. And this doesn't depend on the lifting you choose. And so here we just lift it to OCK. And then we apply the formula, and then we take bar. And then let's write it more clearly. Passing to the limit. And we got theta x is summation of n p to the power n x n n. Okay, quite satisfying. Remark. For any x in the weight ring, let x n R such that small x is addition of p to the power n x n this is a Teichmuller lift, so this lies in WR, so this lies in WR. It's easy to realize this actually. We call this, we can compute with this x actually. First we call this the Teichmuller representation. Of x, and xn is called the Teichmuller representative of X. Actually, you could compute that. If this is your X, then this is just x0 plus 0 plus, right? This is just Teichmuller relative of x0 plus p times p is washable and Frobenius. So p times pth root of x1 p squared times p squared root of x2, etc. xn is should be just the nth root of x n nth root of the x of x. Understand what I'm saying, right? So theta is a ring map, imply that theta of x is theta of summation n p to the power n x in bracket, and so this is n p to the power n theta of xn. Theta of xn is just by the formula xn 0, because there are no other terms. This is theta of x 0 and then 0 elsewhere. And so in that kind of homogeneous polynomial, there's only one term, which is x and 0 itself. So finally, this is summation p to the power n times x and 0. With theta of x and yeah, this is x and theta of x and wait, this is so this is in WR, so xn itself is in R. We apply theta on W of R. Yeah, by the formula, you're taking the zeros composition of this xn. This xn is x and R, and you take its x and 0. Yeah. So how do you got this from x? X is x0, x1, etc. And from there, your xn is furthermore xn are far bigger than 0. In theory, you select out this x and 0. So it's like there are two level of things. Exercise 4. Theta is surjective. truth. For any element in OCK, there exists an element in R such that x0 is A, because you just continue to take pth roots of it. And we know this is algebraically closed. And now you just consider x to be x and with 0 elsewhere. Then under theta by our formula constructed, this is mapped to summation n p to the power nx n of 0. And this will give you only the first term now 0, and so p to the power, which is x. So wait, yeah, sin WR select for x0, x1, x, and so only this x1 is there. This would be just x0 times 1, which is A. So this is surjective.